Hi everyone and welcome. Today, NORC at the University of Chicago, in collaboration with the UCLA Center for Health Policy Research, will be presenting a course on applying imputation to achieve fair representation when analyzing survey data. We will be looking at how we can handle missing data to ensure that our sample results correctly reflect the target population. Before we dive in, let me quickly introduce myself. My name is Mamadou Diallo. I am Principal Data Scientist at NORC in the Statistics and Data Science Department. I also want to acknowledge that this work is a team effort representing the collaboration of colleagues at NORC and at UCLA. What is fair representation and why does it matter? Fair representation is the cornerstone of valid research. It means that the groups we are interested in, whether defined by race and ethnicity, income level, geography, and other characteristics, are properly reflected in our data. Missing data is expected in any survey, and importantly, data rarely goes missing completely at random. It often happens in patterns. For example, individuals in low-income brackets may be harder to reach for a survey, or they may be less willing to answer questions about their finances. When this happens, their voices and experiences are systematically excluded from the dataset. This can lead to biased results and poor policy decisions. This is where imputation comes in. It is a statistical method we use to address item-level missing data, with the specific goal of reducing the bias caused by missing data. To handle missing data properly, we first need to understand where it comes from. As you can see here, we break it down into two main types. First, there is unit non-response, which is when all survey variables are missing for a particular record, or the available data for the record is deemed not sufficient to inform the research. A simple example is when someone was selected for a survey but refused to participate. We have no data for them. Today, we will focus on the second type, which is item non-response. This is when some but not all of the data is missing for a particular record. The person participated but may have left a few questions blank, perhaps because they did not know the answer, or perhaps they refused to answer sensitive questions, or accidentally skipped a question. This table shows that missingness can be planned or not planned. For example, a deliberate skip pattern in a survey is a form of planned item non-response. But more often it is not planned and is a consequence of things like refusals or data entry errors. The last column shows typical approaches for handling missing data. For unit non-response, the common fix is reweighting the data. But for item non-response, the main interventions are imputations or deletions. Simply deleting the data can throw away valuable information and introduce bias. In this case, imputation becomes our primary tool for ensuring fair representation. This is what we will be discussing in the rest of the course. The right way to handle missing data depends on the type of missingness. Let us classify the type of missing data into three categories. First category is missing completely at random. This is when the probability of data being missing is the same for every record. The missingness is not correlated to any of the observed data. This is the simplest scenario, but it is the least common. Second category is missing at random. This means the probability of data being missing is the same within groups which are defined by the data we observed. For example, if men are less likely to answer questions about depression, the missingness depends on gender, which we observed. The MAR assumption is fundamental to most standard imputation methods. And lastly, we have missing not at random. This is the toughest scenario. It is when the missingness cannot be explained by any of the observed data. The classic example is when people with very high income are less likely to report it. In this case, the missingness depends on the value itself. So, how do we figure out if our data is missing completely at random or if we have evidence for MAR? This slide outlines several methods, formal and informal, we can use to investigate the type of missing data. The first method, Liddell's MCAR test. This is a formal statistical test that compares the pattern of missing data you observe with the pattern you would expect if the data were truly missing completely at random. A significant p-value, meaning a p-value above the threshold, is strong evidence against the MCAR assumption. The second method is a collection of t-tests and chi-square test. These are simpler tests you can run on a variable by variable basis. You can use a t-test to compare the average of continuous variables like income between groups. Similarly, you would use a chi-square test to do the same for categorical variables like education levels. If you find a significant difference, it suggests that the data is not missing completely at random. A third method is the logistic regression. This is a very powerful approach. You essentially try to predict the missingness. You create a binary variable, 1 for missing, 0 for observed, and use your other variable to predict. If you find that any variable is a strong predictor of missingness, you can effectively rule out the MCAR assumption. Lastly, we can use visual diagnostics. Before running any formal test, it is always a good idea to just look at your data. You can create box plot or bar chart to visually compare the distribution of your variables between the groups. Often, you can spot differences just by eye, which give you a good starting point for your formal testing. When we decide to impute, there are two main groups of methods, which are single imputation and multiple imputation. For single imputation, we generate only one value to replace the missing data. However, for multiple imputation, we generate at least two values to better estimate the variance. Regardless of the selected method, at its core, imputation is a modeling exercise. Its success depends on having good covariables. These covariables should be related to the variable you are trying to impute or to the missingness mechanism. The assumptions of your imputation model must hold for the results to be valid. On this slide, we list common imputation methods. We can start with mean, median, mode imputation. These imputation methods replace the missing value with a statistic such as mean, median, or mode using the observed value for that variable. For example, we may replace a missing income value with the mean income of the observed data points. Hot deck imputation replaces missing values with observed values from similar cases coming from the survey based on matching characteristics. Cold deck imputation is similar to hot deck. It replaces the missing values with values from external sources. For example, we may use cases from administrative sources or previous round of the survey to impute. Regression-based prediction uses regression models to estimate missing values using other variables in the data. Machine learning models apply algorithms such as decision trees and random forest to predict missing value based on learned patterns. On the table, you will find Some pros and cons of single imputation. Some of the pros of using single imputations are the following. The method is simple to implement. It also leads to only one complete usable dataset. On the con side, we can mention these points. The method underestimates the true uncertainty of the estimates by not accounting for the additional variability introduced by imputation. Also, it can distort relationship between variables. We can further divide the single imputation into two groups, deterministic versus stochastic, or random. Deterministic imputation produces a fixed imputed value every time the process is repeated. While simpler, this approach can underestimate uncertainty and distort the variable's distribution. Stochastic imputations, on the other hand, adds a random component. Therefore, it does not necessarily produce the same value every time. This is better at reproducing the correlation between variables. But you must be careful that it does not create implausible values. Another way to classify imputation methods is by where the imputed value comes from. Donor imputation assigns an observed value from a similar record called the donor to the missing record called the recipient. Methods like hotdeck fall into this category. The advantage of donor imputation is that the imputed values are guaranteed to be plausible because they were actually observed. It is also convenient when imputing multiple variables, since the donor can be used repeatedly. The alternative is predicted value imputation, where a model generates a value based on other observed variables. This includes regression and machine learning methods. This approach is very flexible, but it depends heavily on the validity of the model. To choose a model, you should rely on a rigorous selection process and explore the following questions. Do you have appropriate set of covariables that are related to the variables you are trying to impute? Second, what is the relationship between the variable to be imputed or the missingness mechanism to covariables? In the case of complex or nonlinear relationships, a non-parametric model might be useful. When fitting your regression or machine learning models, take precautions to minimize the risk of overfitting or underfitting. Given the survey context, we must consider whether the sampling design affects the missing data mechanism. If the design is informative, meaning the probability of selection is related to the missingness mechanism, standard imputation may introduce bias. In this situation, incorporating survey design features such as survey weights or stratification indicators into the imputation model may help. If the sampling mechanism is non-informative, the imputation model may only need to generalize to the sample. If it is informative, on the other hand, we need to ensure that the imputation model is valid for both the sample and the population. This distinction is often overlooked, but can introduce biases. How do we know if the imputation model is reliable? We can use common tools such as outlier detection and residual plots. We can use diagnostic statistics. We can do cross-validations or use information criteria for model selection. For machine learning models, we use techniques such as training versus testing sets, k-fold CV, or permutation importance. Donor imputation methods are often recommended for categorical variables because they preserve the variable distribution and avoid creating unrealistic values. This is especially important in multi-level or weighted survey data where the representation matters. As discussed previously, single imputation methods do not properly reflect the uncertainty because the predicted value is treated as observed. Multiple imputation is the default approach for accounting for the additional uncertainty due to imputation. The multiple imputation approach involves creating multiple complete versions of the data. Then, we combine the individual results from the different data sets according to the Rubin's rules to derive the final estimate. The data replicates allow us to estimate the additional variance due to imputations using Monte Carlo techniques. By their nature, multiple imputation methods are random. There are important practical issues to manage when using multiple imputation. Here are a few to keep in mind. First, let's talk about the analytical files. You need a strategy for how to store, handle, and communicate the multiple imputations. The standard approach is to generate and store multiple complete datasets, each with a different set of imputed values. An alternative is to store the imputation model itself. This allows an end user to generate the imputed dataset on demand, which can be particularly useful in secure or remote computing environment. Regardless of the storage strategy, it is crucial to provide clear guidelines for anyone who will use the data. The guidelines should explain exactly how to produce estimates using the dataset. The good news is that there is a wide availability of software for multiple imputation. Multiple imputation is supported across all major statistical platforms. Here is a list of libraries commonly used to perform multiple imputation using survey data. Finally, what is the number of imputation needed? Here we refer to that as M. A common rule of thumb, first suggested by Rubin in 1987, is that 3 to 10 imputations is typically sufficient. However, for more accurate estimates, especially when the fraction of missing data is high, more imputations are needed. This formula on the slides gives a more formal way to guide the choice of M based on the fraction of missing data and the coefficient of variation. Now we are going to make this presentation more concrete with a simple case study. Imagine we have a small survey of 20 people. The survey dataset has the following variables: ID, education achievement, employment status, and income. However, 3 of the surveyed people did not provide the income. Therefore, we have missing data. Our goal is to estimate the average income of this study. The first step in any imputation task is to understand the data, the nature of the missingness, and the response pattern. Normally, this would involve a thorough exploratory analysis to test whether the data is missing completely at random, missing at random, or missing not at random. However, given the scope of this presentation, we will proceed by making the following assumption. We will assume that income is missing at random, which, as we discussed, mean that the missingness on income can be explained by other variables we observed, in this case, education and employment status. With that assumption in place, our next step would be to investigate the relationship between income and these covariables to help us identify and prioritize a specific imputation method. For step 2, we perform imputation using a random hot deck method. We use the predictor variables, education and employment, to define pools of donors for each missing record. Donors are the individuals with observed income values who share the same education and employment status as a record with missing data. Then we randomly select a donor and use their income to replace the missing data. We repeat this process to create M-complete datasets. In this example, we choose M equal 5. We can see the results in the table. For each of the 3 records with missing income, we now have 5 different plausible values, one for each imputation. In step 3, we use the 5 complete datasets for estimation. We calculate our statistics of interest, in this case, the average income, for each of the 5 datasets. Then we pull these results using Rubin's rules for the mean and variance. You can see the formulas on the slide. This gives us a final estimated average income of $2,340. Furthermore, this method provides a standard error that properly accounts for the uncertainty due to imputation. So let us wrap up with the key takeaways. Imputation is a tool for ensuring fair representation by reducing bias from missing data. Not all missingness is equal. Understanding if it's MCAR, MAR, or MNAR is critical. Method choice matters. Single imputation is simpler but can underestimate uncertainty. Multiple imputation is generally preferred because it better reflects the uncertainty. Good covariates are the key to a successful imputation. Remember that imputation is a form of modeling, so its assumptions must be defensible, and the model should be validated. Finally, transparency is crucial. You must be clear about the methods and assumptions used, especially when dealing with data related to fair representation. For those of you who want to dive deeper into the theory and methods, this slide provides some of the key publications in the field of missing data analysis. We are now at the end of this presentation. I thank you for your time and attention.